A-Level Physics, Lesson 42, Motion Graphs. And for this lesson and the next lesson, it's going to feel a little bit like treading water because we're not covering a lot of extra ground compared to GCSE level. But we'll do it anyway because it's the right thing to do. Let's start by talking about the difference between distance time graphs and displacement time graphs. So distance time graphs will always be in the first quadrant of a graph. It'll never make any sense to have the second quadrant, or the third, or the fourth. So time and distance. Now the reason for that is it's impossible to reduce distance. You can't do it. So a distance time graph will always show an increase, never a decrease. So always show an increase. Whereas a displacement time graph, and I'll draw that next to it, can show a decrease because you can reduce displacement. Time and displacement. Remember that displacement is a vector and distance is a scalar, and this is really the reason why. So if we have a displacement time graph that does something like this, and the corresponding distance time graph, and this isn't going to be to scale on the, well, it will be to scale, but it'll be scaled down on the y-axis, is going to go up like this, and then carry on going up like this. And they show perhaps equivalent motions. They show the same thing. Because what's happening here is when the gradient is steeper, we have a larger speed. So let's make a point of that for both higher magnitude gradient means higher speed. And that is absolutely true. And we can also say that the magnitude of the gradient is equal to the speed for both. So we could say, try and get this right, magnitude of gradient equals speed. That is true for both. Now, for the left-hand graph, the gradient's always positive or zero. It's never negative because you can never reduce the distance that you have traveled. If the gradient is zero, that means that we have a velocity of zero. We've stopped moving. And that is the case here as well. So both of these graphs actually could be used to show the motion of something which has been thrown in the air. These two graphs, both of them show a ball thrown in the air. And so what do we see? The ball goes up at the beginning, the ball goes down at the end. And at some point in the middle, the ball is stationary when it's at its highest height, its greatest displacement from where the ball was released. And yet on a distance time graph, the ball's going fast, the ball stops, the ball's going fast again. It doesn't undo the distance it's traveled. And that's so, so important. And these are equivalent graphs. So we could say a few other things. We could say that the gradient of a displacement time graph that is the velocity. So if the gradient is increasing, then the velocity is increasing. If the gradient is decreasing, which is the case here, then the velocity is decreasing. And that is exactly what we see here. So that is one of those super duper important facts to remember, that the gradient of a displacement time graph is the velocity. Absolutely crucial. But you should also remember that the magnitude of the gradient for either of these graphs is the speed. That is true. So that's distance and displacement graphs. What about velocity and speed and velocity graphs? So speed versus time and velocity versus time. So let's draw those two graphs. Let's see if we can make sense of these. Now, speed can decrease, but it can't become negative. Can't have negative speed, whereas our velocity can become negative. So on our velocity time graph, actually, as with our displacement time graph, we can have data in the second quadrant. So let's label the axes. Let's label this one speed. I've got the wrong pen. There we go. Come on, pen. Speed versus time. And this is going to be velocity versus time. Okay, so if we have a speed versus time or a velocity versus time, let's start with the velocity versus time. And let's say that we are throwing our ball in the air. And the velocity starts positive, but it decreases over time, and then it becomes negative. And in fact, I've tried to draw it so these graphs, they line up. I've tried to draw it so that the instant in time when our velocity is 0, I missed. Didn't quite get it right. So let's just manipulate some of this a little bit to make it show what I wanted to show. And then we are going to, yeah, that's good. And then I'm going to get out my eraser and erase that part there. So they are showing the same instant in time right there, which is where the velocity is 0. And they're showing the same situation. All four of these graphs at the moment are showing the same situation. So now let's draw our speed time graph, showing the same situation. Well, the speed is going to be reducing to some point, and then it's going to be increasing again. And the gradient, or so to say the magnitude of the gradient, is going to be the same for both. And again, let's try and draw. Oh, I was much more successful that time. Look at that. Much more successful. And now let's erase this part here. Lovely. So these four graphs show the same situation. They all show a ball being thrown in the air. This is what they all show. A ball being thrown in the air. So higher gradient would be higher acceleration. We should probably say this for velocity time graphs. For velocity time graphs, the gradient is the acceleration. And you can see that the acceleration is the same at all points here because the ball is in Earth's gravity. It's been thrown up in the air, but it's accelerating down the whole time. That's why it's a negative gradient, negative acceleration. Our initial velocity is positive, so we're defining up as positive. And therefore down is negative, so the gradient of this is negative because we're accelerating in the opposite direction to our initial velocity. Of course, after we've reached the very top of our path of the ball's then going to be falling, and so its velocity will be down, and so will the acceleration. And that's why they're both negative. So everything follows on these graphs. These four graphs show the same situation. So let's get some more equal signs, just to show that that is equivalent to this, and actually that is equivalent to that, and that is equivalent to that. I don't know if that's a notation that I'd ever choose to use, but they are showing the same thing, which is the ball being thrown in the air. So for velocity time graphs, the gradient's the acceleration. What about for speed time graphs? Well, the gradient is negative here because we are slowing down. So we could say that the magnitude of that gradient is the deceleration. We could say that. What about here? Well, we couldn't really draw any conclusions from the gradient there. Yeah, the speed is increasing, so it's not decelerating. But we don't know whether the acceleration is positive or negative from this graph alone. It doesn't have any direction information. So all we can say is that the speed time graph, so for speed time graph, when you say velocity time, speed time, the first thing is on the y-axis, the second thing is on the x-axis. This is a pretty standard way of notating graphs or describing graphs. So for speed time, only reduction in speed is interesting, which is equal to the deceleration. Well, I should say the gradient equal to deceleration. The other one is, all you know is the magnitude of the acceleration. So gradient equals to deceleration, or magnitude of gradient, let's say. Well, we usually indicate magnitude by doing bars either side. So let's write that equals deceleration. But the increase, this part here, just gives us the gradient of that is just the magnitude of the acceleration. So velocity time graphs far more useful because the directionality. Okay, fine. There's other information that we can pull out of these graphs. So for velocity time graphs, let's do it like this, sorry. For velocity time graphs, the area underneath is going to be the displacement. So let's put this here, area under, and when we say under, we mean between the line and the x-axis. So under, between line and x-axis. So the area under is equal to the displacement, S. Now, that could be positive or negative. So area equals S, I've already said that, and is positive if above, that's not how you spell above, if above x-axis, and is negative if below x-axis. So the total displacement here is going to be 0 because this area is going to be equal to this area. Well, that makes sense because we catch the ball. We're throwing the ball in the air. The ball is slowing down, slowing down, slowing down. It stops, and this area here will be the maximum height the ball reaches. And then the ball descends the same distance because it lands back in our hand. So let's actually indicate that that is the maximum height of the ball. Just like this, that area equals maximum height of ball. Let's choose a different color. And yeah, let's area equals maximum height of the ball, like that, and it should descend the same distance in order to have a displacement of 0 at the end. And we know that must make sense because we start at a displacement of 0, we end at a displacement of 0. But this value here, this displacement, will be equal to this area there. Okay, well, what about the area under a speed time graph? Well, that's the distance. It never goes negative because the distance always increases. Never decrease distance. So we could say that the area under and I've already said it's between line and the x-axis, speed time graph is distance. And it's a scalar. Scalar only tells us the distance. So you can see that the distance is increasing, but in decreasing amounts until there, where the distance doesn't increase for a bit, which is what we've got there, and the distance continues to increase, which is what we see here. And as we move along the x-axis of the speed time graph, approaching the green line, the amount of extra distance is smaller and smaller and smaller each time, which is why this is curving like that. And then as we carry on away from the green line, the amount of extra distance, the amount of area we add each time is getting bigger and bigger and bigger, which is why this curves that way. So it all works. It all makes sense. Let's just get rid of my arrows, my doodling. And there really isn't much more to say. If you have a ball that's bouncing, then you might have negative velocity to start with if the ball is descending at the start, but it might not reach the same height. And you'll know it won't reach the same height because the area after the bounce will be less than the area before the bounce. And you could even calculate those areas and use that for the displacements. And then you could use a GCSE equation like E equals mgh. You've got a difference in height from before the bounce to after the bounce, so you can calculate the loss of energy in the bounce. And there's all sorts of things like that that you can do, putting together the pieces from GCSE level and A level. But actually, that really is all I need to talk about for distance time graphs, displacement time graphs, speed time graphs, and velocity time graphs. So we've got all this empty space at the bottom for notes that I didn't need to take because I think that's probably enough. Right, now short lesson. Like I said, we're going to be treading water for a little bit because we're just mopping up some GCSE stuff. So next lesson, we'll look at how to do calculations on motion along a straight line. But again, it's pretty straightforward stuff. Hope you'll join me then.